Hello there, you're on Vectorly, and today it's all about rotational dynamics. Today we are going to solve some four set of problems from rotational dynamics, which is taken from Pathfinder. These problems are good enough for a student to attempt JEE. Okay, let's go to question number one. A uniform disk rotating about its vertical axis of symmetry is gently placed on a horizontal floor with one of its flat face on the floor. The floor has two portions where coefficient of friction is different, which is mu1 and mu2. Okay, consider the line dividing the two portions as y-axis and the point where the center of the disk is placed as the origin of a coordinate system as shown in the figure. Find acceleration of the center of the disk immediately after it is placed on the floor. So what happens is we are placing a disk which is rotating about its vertical axis on a horizontal floor which has two different surfaces. Okay, because they have two different coefficients of friction. Okay, so now what happens is at each and every point, let's take some point over here. The friction would be perpendicular to the radius vector. Correct? Okay. Now what happens is this overall friction generates an anti-clockwise torque. Okay. But what are they asking? They are asking the acceleration of the center of the disk. The acceleration is caused only due to friction. So we have to find the acceleration due to friction. Okay. Because it's placed on a horizontal floor, so gravity does no work. Only friction does the work. Okay. Now, if you take friction dF acting in this direction for a particular part subtending d theta angle. Okay. Let's take two components. So which is Fy and Fx, which is the net frictional force in y direction and x direction. Now for Fy, we have to integrate df cos theta and Fx, we have to integrate df sin theta. Okay, by convention. You can check it later. Now, what happens is if you think properly, let me erase these things. At this particular point, let's take 2 points symmetrical about x-axis. At this point, velocity is in this direction, so friction will be in this direction. Okay, at this point, velocity in this direction, so friction will be in this direction. If you take these 2 points, the x component, this magnitude will be same because same coefficient of friction and same mass and same values. Okay. Now what happens is the as we are taking the same angle, the x component will also be same but in opposite direction. So the x component gets cancelled. So on overall, these two parts, the x component of these two parts on overall gets cancelled by intuition. Similarly here it gets cancelled. Okay. So on overall thing, what happens is this df sin theta becomes 0 by intuition. Now you can think about it later. What if mu1 and mu2 are equal? The overall friction force will not generate linear acceleration. It will only generate angular acceleration. Okay, that thing we will get conclusion if mu1 and mu2 are equal. Now the only thing we have to calculate is Fy, that is integral of df cos theta. So let me tell how are we going to integrate df cos theta. Okay, now what about df? What is df? Df is nothing but the coefficient of friction there into normal reaction, which is dn. So what is normal reaction here? It's just its weight, right? So mu into what is dn? Dn is g into dm. Okay. Now mu g, what is dm? So this dm is small mass over here. So let's assume the density to be sigma. Okay. And thickness to be t. And the area of this particular sector is half r square d theta. You might have learned it. Or you can just derive it by using, because pi r square area is under 2 pi radians. So what about in d theta radians? So divide by 2 pi, multiply by d theta. So you get half r square d theta. Okay. So dm is nothing but sigma t into half r square d theta. Okay. Now what happens is df is nothing but I'm taking this whole part as K. Okay, K d theta. Now I have to integrate. Force in x direction is nothing but integral of df into cos theta. So K cos theta into d theta. Let me consider this. Without mu, I am considering it as K, because mu value changes. It's not a constant for entire angle. Okay, so I'm just considering mu over here. So between 0 to 2 pi, but mu varies, right? So what I have to do is, let's take the range, which is minus pi by 2 to plus pi by 2. What is the value of mu? It's mu 1. So mu 1 k cos theta d theta. Okay, plus from pi by 2 to 3 pi by 2, you get mu 2. So mu 2k cos theta d theta. If you integrate this is simple cos theta integration, you can do it. Okay, let me give you time. And what about the acceleration due to friction in x direction, or acceleration due to friction because it's only in I cap direction? Okay, so acceleration vector in x direction is nothing but fx by dm, not dm, the integral of dm. Okay, how are you going to integrate dm? It's simply mu, sorry, not mu, it's simply sigma t into overall area, which is pi r square. So we have to divide it with this value, which is dm. Okay, I'm putting this in brackets. If you divide it, you will get the final answer which they are asking. Okay, the just think about this thing where mu2 and mu1 will be equal, and try to imagine this situation, because imagination helps in JEE Advance. See you in question number 2. Question number 2. In a free space, an assembly of two identical particles, each of mass m, connected by two identical uniform ropes, is rotating at a constant angular velocity omega about an axis passing through the center of the line segment joining the particles. The ropes fan out due to inertia and assumed a curved shape as shown in the figure. If distance between the midpoints of the rope is d, tensile force at the midpoint of the rope is t, sorry, that is d and this is t, and the included angle between the ropes at the particles is theta, find the distance L between the particles. Okay, so what happens is, these two are two different particles. Let's suppose this is P1 and this is P2. Now we are just rotating these two particles. Sorry, we are just attaching these two particles with the help of a rope, and just we are rotating with respect to this point. Okay, now these things, let's consider this whole thing as system, and this revolves with a constant angular velocity omega. Now what are they asking is, at the midpoint the tension is T, okay, and this distance is D. So what are they asking is, find the distance L between the particles. Okay, so this is the distance L between the particles. Okay, I'm just marking from center, it's L by 2 by symmetry. This whole system is symmetric, right? So by symmetry it's L by 2. If the distance between the midpoints of the rope is D and the tensile force at the midpoint is T, so at this particular point, let's assume this to be T naught. Okay, let's assume this to be T naught, and by symmetry this is theta by 2, and by vertically opposite angle this is theta by 2 again. So they are asking, okay, the distance L. Okay, now let's calculate this. I'm just dividing it into a quarter. Okay, the tension at the midpoint is T and the other point is T naught by 2, which we have found. We have to find first what is theta T naught. Okay, so if you see, they have mentioned somewhere over here, it's moving with a constant angular velocity. So net torque is 0, right? The net torque of this system is 0. So the torque due to these tensile forces, in between all these forces will get compensated. Tensile force, if it's acting here, is T1. Here also it will be T1. I'm just cutting this part, right? So I'm considering this quarter. So on overall, the torque due to this tensile force is 0. So T into d by 2, perpendicular distance from center of rotation. This is the torque due to this. Should be equal to the torque due to this. So which is T naught into, if you see this torque is in this direction, this force is, and effective force is in this direction and the effective force is in this direction. So this generates an anti-clockwise torque and this generates an clockwise torque. So T naught, the component of T naught perpendicular to this is nothing but T naught into sine theta by 2. Okay. Into perpendicular length, which is L by 2. Okay. If you just equate it, what you get is, what is T naught? T naught is nothing but T by sine theta by 2. Okay. Into D by L. Okay. These half gets cancelled. So this is what T naught. Now what happens is, if you see from this body is likely undergoing a circular motion about this point, right? Simple. So what happens? This must have some centripetal force. Okay, you know the omega 2. So this centripetal force I'm terming as Fc. Okay, this Fc is nothing but, let's assume the mass of this ball is m. So m omega square into r. So here r is L by 2, which is, this is not a fictitious force. Centripetal force is not a fictitious force. Some kind of force will be acting towards center. Here it's tension. No other force is acting. So the component of these two tensions along this direction, which is 2, okay, T naught cos theta by 2. Okay, and we know the value of T naught 2. So what are they asking? They are just asking the value of L. So 4 cos theta by 2 whole divided by m omega square. What about T naught? So T naught is nothing but T by sine theta by 2 into D by L. So if I multiply this L over here, I get L square is nothing but 4 cos theta by 2 into T into D whole divided by m omega square sine theta by 2. Okay. So at last of these kind of questions, you must verify this thing. All the things in the answer should be given. Your assumed terms should not be included over here. Okay, because if I do so, I can directly put this equation as my answer, but I don't have T naught because I assume this T naught. So you have to find another relation for T naught in terms of the given values. Okay, given variables. This is an important part in our question. Some people will confuse between T naught and T. Okay, and will write it directly as, you won't get this particular part of the question. Okay, if we are not getting this question is completely wrong. Question number 3. An almost inertialess plank AB can rotate about a stationary horizontal axle O. Its end B rests on a platform where a small block of mass M is placed on it, at a distance L from the axle as shown in the figure. A bead of mass M0 dropped from a height H0 hits the platform near the end A at a distance L0 from the axle. If all the collisions are perfectly elastic and every object is perfectly rigid, find the height h to which the block will jump. Okay, in this case, what happens is this plank is inertialess, which means it doesn't have any mass. Okay, mass is negligible. Okay, some fancy term is inertialess. Okay, here what happens is we are just dropping this ball. Okay, and there is a small block of mass m. This is m0 placed at a height mh0, and the cohesions are perfectly elastic, and there is no friction also. Okay, and they didn't mention it here because there is no use of friction here too, so there is no loss of energy, so we can conserve energy over here. So conservation of mechanical energy applies. And this system, the overall system consisting of this plank and these two bodies, doesn't have any external force which creates some external torque, so we can conserve the angular momentum too. Okay, just before the collision, the value of this velocity of this particular ball, m naught, let's assume to be u naught. So the value u naught will be root over 2g h naught. So this is the standard result, okay, by conserving energy or kinematic equation. So we have this thing. Just after the collision, let's assume this particular plank rotates with an angular velocity omega just after it. And this moves downward with velocity v1 and this moves up with the velocity v2. So we have v1, omega and v2. So we have three variables, but we have only two equations. What is the third equation? The third equation hides here perfectly elastic. So the third one is coefficient of restitution, which is E. As this is a perfectly elastic collision, E is 1. So velocity of approach is equal to the velocity of separation. So what is the, let's consider here as two collisions, the collision between these two and the collision between these two. So the velocity of approach over here is nothing but v1, which is equal to the velocity of separation. Just after separation, if this goes with omega into L naught, this goes down. So v1 minus omega L naught. Okay, sorry, here it comes u naught, okay, which is under root 2g h naught. From this we can get omega into L naught is nothing but v1 minus root over 2g h naught. Okay, and over here this is part 1, collision 1. What about collision 2? In collision 2 the velocity of approach initially is 0 because these two are together initially. What about the separation? Separation velocity is v2 minus omega into L. Correct. So from this we can write v2 is nothing but omega into L. This is a very important part of this question. We found omega in terms of v1 and v2. Sorry, here the velocity of separation should be v2 minus v1. So I have to put negative sign over here. Okay, so if I put negative sign over here, again this becomes positive, and if I bring it here, this becomes negative. Okay, now let's conserve angular momentum. So if we conserve angular momentum, what we get is initial angular momentum anti-clockwise is positive. So this generates an anti-clockwise thing. So m naught into under root 2g h naught into L naught, which is initial angular momentum, equal to the final one. What is the final angular momentum? So m naught into v1 into L naught, okay, plus m v2 into L. Okay, so m naught into under root 2gh L naught should be equal to m naught L naught. What is v1? v1 is nothing but from equation 1 omega L naught minus under root 2g h naught plus m v2 L. So m omega L square. Okay, so this thing goes over here, the same thing repeats. So 2m naught under root 2gh L naught is nothing but m naught omega L naught square plus m omega L square. So if I take omega common from this, I can get omega is nothing but 2m naught into under root 2gh into L naught whole divided by m naught L naught square plus m L square. Okay, so this thing gives the equation of omega. Now what next? We have to find the value of v2. So what is v2? v2 is from equation 2 you get v2 is omega into L. So if I multiply this with L, we get v2. So 2m naught under root 2g h naught, sorry, h naught into L naught L whole divided by m naught L naught square plus m L square gives v2. Okay, now what is the h max? H max is nothing but v square by 2g. So v2 square by 2g. So if you just square it and divide by 2g, you get the final answer, which is the maximum height reached by this particular block M. Question number 4. Two identical disks, each of radius r and mass m, having plate-like light protrusions, are coaxially mounted on a thin vertical pole that is fixed on a horizontal floor. A small spring of force constant K is affixed on the protrusion of the lower disk as shown in the figure. The upper disk is given an angular velocity omega naught and gently released on the lower disk. Friction is absent everywhere. Find the maximum compression of the spring and find the angular velocities of the upper and lower disks when the spring becomes relaxed. So now this question is nothing but this have some external protections. So protrusions, between these two protrusions there is a spring placed. Okay. Now if you just release this, due to gravity this comes down, and this is initially moving with an angular velocity omega naught. This moves relative to this. Okay, there is no friction, so we can conserve energy. No other external force, no other work done, so we can conserve energy at first. Also, there is no external torque, so we can conserve angular momentum in this question. We have to find out these 2 points. Sorry. In every question, if you see, you have to fetch which things we can use. These are methods of solving a question. Conservation of energy, conservation of angular momentum, that coefficient of restitution, all these things are helpful in solving questions. You have to have a checkbox for these. To conserve energy, there should be no external work done. To conserve angular momentum and to conserve linear momentum, there should be no external force or torque. These things should be found written at first. Okay. At this question, there is no external torque. Okay. So we can conserve angular momentum. The upper disk is given an angular velocity omega naught. So initial angular velocity is omega naught. Let's assume this both are identical, right? So the moment of inertia of this is I and this is also I. So what is the value of I? We know it half mr square. Let's keep it aside. Okay. You can assume the required variables to minimize your writings. Okay. Now what happens is let's conserve the energy first. Let's do the first question. A. Now initially what energy does this have? Only the rotational kinetic energy. So half I omega naught square. But what about the final case? At this particular situation, when they are when the spring is at maximum compression, when the spring is at maximum compression, there may be two cases in which both have zero relative velocity. In both cases, these two have relative velocity. Okay, if they have zero relative velocity, they may move with a common angular velocity omega, or they may be in rest. Okay, so we can assume it as omega. If omega is 0, then this case also gets satisfied. So now half into 2i, this combined system is moving with an angular velocity omega, and that part kinetic energy plus the spring potential energy. So half k into x squared. Okay, if I cancel all these half parts, what I get is I omega naught square is nothing but 2i omega square plus kx square. So they are asking the maximum compression. How are we going to find? We need this omega, right? So let's conserve the angular momentum. So how will we get this angular momentum? So initial I omega naught is nothing but final 2i into omega. So omega is nothing but omega naught by 2. So if I substitute here, what I get is I omega naught square is nothing but I omega naught square by 2 plus kx square. Sorry. So from here I can get I omega naught square by 2k is x square. So this is the maximum compression of the spring in first case. Now in the second case, again the spring becomes relaxed. So these two have different angular velocities. The spring will exert force, equal force on these two particles, right? So this will experience some force and this will experience some force. This will get some torque, this will get some torque. As we are considering this as whole system, no external torque is there. So we can conserve angular momentum there too. Okay, so let's assume this moves with an angular velocity omega 1 and this has angular velocity omega 2. Okay, now what happens is if we conserve angular momentum, I omega naught is nothing but I omega 1 plus I omega 2. So from this you get omega naught is equal to omega 1 plus omega 2. So this is equation 1. What about the second case? Let's conserve energy. So if we conserve energy, half I omega naught square is equal to half I omega 1 square plus half I omega 2 square, and the spring is relaxed, so no energy in spring. So omega naught square equal to omega 1 square plus omega 2 square. So if we replace any of the ones, omega 1 with omega 2, so what we get is omega 1 square plus, what is omega 2 square? Omega naught minus omega 1 the whole square. So omega 1 square plus omega naught square plus omega 1 square minus 2 omega 1 omega naught. So this omega naught square gets cancelled over here. So what we get is 2 omega 1 square equal to 2 omega 1 omega 2. So omega 1 square minus omega 1 omega naught is 0. So omega 1, if I take common, omega 1 minus omega naught equal to 0. So if you see, what happens is two cases can be considered. Omega 1 is 0 or omega 1 is omega 2. If you see, if omega 1 is 0, sorry, if let's consider if omega 1 is omega naught. If omega 1 is omega naught, it's simply the first initial case itself. And this thing, the omega 2 will be 0. So it's exact the same case in which the spring is also relaxed. All these conditions satisfy. But this is after, just after the compression. So that is not the case. So we can completely say this is not the case over here. This is just before the spring compression. So the only possible case is omega 1 is 0 and omega 2 is omega naught itself. So we found the angular velocities of the upper and lower disk, where the upper disk comes to rest and lower disk goes with an angular velocity of omega naught in the same direction. So thank you for watching this video. Kindly support our channel.